Hello, this video is going to be about calorimetry and finding the heat of reaction in units of kilojoules per mole reaction, which are some things you commonly see on the AP test. So first, let's take a look at this calorimetry equation. And again, this is on your equation sheet, so you don't need to memorize it, but you do need to know when it's applicable and how to use it. So Q equals m times C times delta T. Q stands for the quantity of the heat that's transferred during a reaction, and sign is going to be important here. So you want to think about is heat being gained or is heat being lost. M is going to be the mass in grams. C is the specific heat. The units are in joules per gram degree Celsius. You might see them sometimes given in joules per gram degree Kelvin. And when we're talking about temperature change, the change in Kelvin is the same as the change in Celsius. So either unit works here, again, because we're talking about a change. And then delta T, that delta stands for change, so it's a change in temperature, and that's the final temperature minus the initial temperature. And the order in which you subtract those is important because that will affect your sign, which is important. Sign is always important to think about when we're talking about enthalpy, because we want to think about it as energy being gained or lost. We want to think about the meaning of specific heat. So that specific heat value, that C value from the previous equation, represents the amount of heat energy required to change 1 gram of a substance by 1 degree Celsius. And if we look at an example here, if you think about when you heat water in a pan on the stove, the specific heat of water is 4.18 joules per gram degree Celsius. The specific heat of metals are typically much lower. Like if, let's say it was an aluminum pan, specific heat of aluminum is 0.9 joules per gram degree Celsius. That tells us it takes about 5 times as much energy to change the temperature of a certain sample of water. So water is going to take more energy to change its temperature. So like when you see this on the stove, the pan is going to get hotter faster than the water will. So that's what your specific heat represents. When we're doing calorimetry, this is a way to figure out how much energy is transferred during a process by measuring the temperature change that occurs during the process. And we've got a picture here of what a calorimetry setup would look like. Typically, you've got maybe some styrofoam cups, you've got a thermometer or a temperature probe in there. You have some sort of stir to make sure the reaction is well mixed. And the important thing to keep in mind with calorimetry is you are always measuring what's happening to the surroundings. So when you're thinking about sign, the Q value that you initially calculate is going to be the Q of the surroundings. And so the Q of your reaction is going to be equal in magnitude but opposite in sign. So if we draw, a little picture right here, and if you imagine like here's your thermometer and in here is your reaction. Your reaction isn't really a thing, it's a process, so we'll draw it as a thing for right now. So let's say that the temperature of the surroundings raise in this scenario. That means the surroundings are gaining energy. That means that your reaction must be losing energy. So in this case, we would observe a positive temperature change, which means the Q of the surroundings was positive. Therefore, the reaction must have lost energy. So like if the surroundings, gained 100 joules in energy, that means the reaction must have lost 100 joules in energy. So in this case, we would see that our reaction's exothermic, so we'd expect to have a negative delta H value there at the end. So again, keep in mind what you are measuring is the surroundings. So the Q of the reaction is going to be opposite in sign of the thing you initially calculate. So we'll look at some examples of that in a minute. Other thing to consider is what mass should you be using? And there's two kind of scenarios that happen when you're doing calorimetry. Scenario 1 over here on the left, where your substances do not mix. This is what you may have done in regular chemistry, where maybe we burned some food underneath a can of water, and you were measuring how much energy the food transferred to the water, and the food and the water did not mix. So in this case, you use the mass of the water alone. What we end up doing a lot here in AP chemistry is finding the delta H of a reaction. So in this case, we're mixing two things together, like maybe combining two solutions or maybe dissolving a solid in water. And in this case, everything is getting all mixed together, and you're taking the temperature of the entire mixture. So you should be using the mass of the entire solution in this scenario. So rule of thumb is make sure you should always be using the mass of whatever you're taking the temperature of. In the example on the left, you're taking the temperature of just the water, so you should use the mass of the water alone. In the scenario on the right, you're taking the temperature of the whole solution that's all mixed together, so you should use the mass of the entire solution. So you might be adding together some masses over here. You might also be using density and a volume rating to determine the mass of your solution. Okay. So let's look at 3 practice problems in which we're going to find the energy per mole of a reaction. So here's a scenario where you're dissolving a solid in water, and a lot of times this dissolving process will actually either gain or release energy. So these could be endothermic or exothermic processes. So we've got 6.5 gram sample of solid sodium hydroxide and 100 grams of water. We observe the temperature of our surroundings increase from 21.6 to 37.8. We're given the specific heat. So we want to calculate the amount of energy transferred during this reaction. So if we see that we've got some values about temperature change and we're asked to find energy, that's our clue that this is calorimetry and we should be using this equation right here. So remember, with the mass, you got to ask yourself, is this scenario 1 where the things stay separate, or is it scenario 2 where the substances mix together? So I'm talking about these 2 scenarios here. And this example is scenario 2. The substances mix together. It tells us that the solid dissolves in the water. So our mass here that we should be using is our total mass. So 100.0 plus 6.5, add that together to get 106.5. Notice in terms of sig figs, I have to stop at the 10th place because my water mass only goes to 10th place. So remember, addition rule, you are limited by the fewest number of places past the decimal. So specific heat, in general, you will see that we assume the specific heat of a solution is the same as that of pure water because these solutions are mainly water. So that's usually a pretty good assumption. And the temperature change is final minus initial. And I like writing out what that temperature change is. You want to be careful with sig figs here, because sometimes like my temperatures might have 3 sig figs, but the change might only have 1 or 2 sig figs. So you want to be careful with that. So we find that Q is equal to 7,210 when I round that to the 3 sig figs. Okay, so now I want to find the delta H for this reaction. So remember, in part A, I found the Q of the surroundings, or sometimes we call this the Q of the calorimeter. So the Q of the reaction is going to be opposite in sign. So if my surroundings gained 7,000 joules of energy, that means my reaction lost 7,000 joules of energy. And it asks us to convert this into kilojoules. So 1 kilojoule is 1,000 joules. So this is negative 7.21. And I want to find kilojoules per mole. And so I want to divide it by moles of reactant. There's only 1 reactant here, so I just have to find moles of NaOH. So I had a 6.5 gram sample of NaOH. I'm going to use the molar mass of NaOH, which is 40 grams, and this is 0.163 moles NaOH. Again, we got 3 sig figs here. So to find the energy per mole, it's negative 7.21 kilojoules divided by 0.163 moles. So that's negative 44.2 kilojoules per mole. Okay, so my steps are find Q, convert it into kilojoules, and divide it by my moles of reactant. Pay attention to sign, pay attention to significant figures, and make sure you're using the right mass value. This is one of the most common mistakes, is right here, getting the right mass value in your Q calculation. All right, let's look at another scenario. This is a scenario where we have 2 aqueous solutions mixing together, whereas before we had a solid dissolving in water. So let's figure out what this reaction is that we're looking at here. So we're mixing together aqueous sodium chloride and aqueous silver nitrate. So let's write out the molecular version of this first. So these are both aqueous. I've got 2 compounds, this looks like a double displacement reaction. So the Na is going to go with the NO3, and I know that's soluble based on my solubility rules. My silver goes with chloride, that's insoluble. So this looks like a precipitation reaction. I've got some spectator ions, so my net ionic equation ends up being aqueous silver ions and aqueous chloride ions will combine to make solid silver chloride. So it's a precipitation reaction. Everything's a 1-to-1 ratio here. And it asks us to calculate the magnitude of Q. And it looks like I've got some temperature values here. So this means I should be using Q equals mc delta T. Okay, so my first step is, what is my mass? So if I look at what's happening here, it's a reaction between two solutions. They're all getting mixed together. So that means the mass that I should use here should be my total mass of the two solutions combined. Looks like it doesn't give me a mass directly, but the problem does give me volumes, and it gives me a density. So it's 1 gram per mil. So that means my 20 mil solution is actually 20 grams. And this 20 ml solution is 20 grams. I mix them together, my solution weighs 40 grams. And I'm told that the specific heat of my solution is the same as that of water. And then my temperature change, notice they both start at the same temperature and they mix together and become 29.6. So my final temperature is 29.60. My initial temperature is 22.0. Thinking about, let's think about our sig figs here. So this is 40.0, this is 4.18, this is 7.60. So notice here, even though my temperatures had 4 sig figs, my change in temperature only had 3 sig figs. So keep an eye out for that. And you end up with a Q being 1270 joules. Okay, and remember, again, this is the Q of the surroundings. So when we're asked here to find delta H for the reaction, the Q of the reaction is going to be, opposite in sign, so negative 1270. Because again, if the surroundings increased in temperature, that means the surroundings gained energy, okay, which means the reaction lost energy. So this is an exothermic reaction. We should end up with a negative delta H here. Okay, so this is negative 1.27 kilojoules. Now let's figure out moles. So in this case, might seem a little trickier because I have 2 reactants given here. I've got silver and I have chloride, so which reactant am I supposed to use? Well, you'll see this happen often. Notice that in the problem, they actually gave us equimolar amounts of reactants. So I had 20 mils of 1 molar NaCl and 20 mils of 1 molar AgNO3. So I actually have an equal number of moles of each reactant. So I could use either value here and be okay. So let's find moles of reactant. And again, it's the same for both. So it's going to be the same calculation for both. It's a 1 molar solution, and I have, make sure my sig figs are right. Yep, I have 20 mils, which is 0.02 liters. So that means I have 0.02 moles of reactant. Let's just say Ag here, but it would be the same for chlorine. Notice they give us equimolar amounts of both. And you'll see they do this a lot on the AP test. So I got equimolar amounts for both. So now I'm just going to take so to find kilojoules per mole, I'm just going to take my kilojoule value, negative 1.27, and divide it by my moles here. So I end up with negative 63.5 kilojoules per mole. Okay, so if I have 2 reactants and they're equimolar, you just use either one of them for your mole value. All right, here is scenario number 3. In this case, I have 2 reactants, but I'm not given equimolar amounts of them. So let's figure out how to handle this one. So we've got a reaction here between hydrochloric acid and solid magnesium oxide. Notice the chlorine does not show up in this reaction because it is a spectator. Okay, in general, you always be given the net ionic equation, so you don't see the chloride in there. And we have some data here in a table. So we are asked to determine which substance is the limiting reactant, and then find the value of Q and find the value of delta H. So we're just kind of adding in an extra step here because they're not giving us equimolar amounts of our two things. So step one, we're going to have to figure out which reactant is limiting, and then we go through and do our other calculations. We want to use our limiting reactant as our mole value down there. Okay, because that's the thing that's actually all going to get used up. The excess is just going to be kind of sitting around. You have extra of it. So let's think through this scenario. So first step, which substance is the limiting reactant? I've got the, let's look at your HCl. So we've got 1 molar, so you got 1 molar HCl, you've got 100 mils of it, which is 0.1 liters. So that means we have 0.1 moles of HCl. And when we're trying to figure out who's the limiting reactant, what I like to do is to compare, pick a product and see like how much product will that reactant make, and whoever makes less product is going to be your limiting reactant. So every 2 HCl's, because that's what this H plus is, this is actually HCl. Okay, just dissociated into H plus ions and Cl minus ions. So every 2 HCl's will make 1 H2O. So this is enough to make 0.1 moles H2O. If you look at your magnesium oxide and you do this calculation, 1 mole of magnesium oxide is 40.3 grams, so you end up with 0.0062 moles of magnesium oxide. In this case, it's a 1-to-1 ratio. So it looks like magnesium oxide will make less product, so magnesium oxide is my limiting reactant. Okay, so let's find the magnitude of Q. So we're using MCAT here. Again, in this reaction, I'm putting something in a solution and they're all mixing together. So I want to use my total mass. 100.25 is my total mass here. My specific heat, they told me to assume it was the same as that of water. And then my temperature change is 26.5 minus 25.5. Thinking about sig figs, this is only a 1.0 degree temperature change. So I only have 2 sig figs in my final answer here. So my final answer here is going to be 420 joules. And remember, that is the Q of the surroundings, so the Q of the reaction is going to be negative 420 joules, or 4.2 kilojoules. And to find the delta H in kilojoules per mole, I'm going to take this negative 4.2 kilojoules and divide it by my moles of limiting reactant. So I find my delta H here is negative 67 kilojoules per mole. So summarizing this, we've got 3 scenarios. Scenario 1 is when finding energy per mole. Scenario 1 is where you have only one reactant. That happens with dissolving. Scenario 2 is if you have equimolar amounts, in which case you could use either mole value when you're dividing. And scenario 3 is if you have 2 reactants given but they're not equal, then you have to determine which is the limiting reactant. And the limiting reactant is the one you should use for your mole value. So that is finding delta H using calorimetry. And let me know if you have any questions.